In this video, we are going to solve example 3.4 that is taken from chapter number 3, Mechanical Properties of Materials, and book name is Mechanics of Material by RC Hibbeler, and its 9th edition. So statement is a bar made of A36 steel has dimension shown in the figure. If axial force P is equal to 80 kilonewton is applied to the bar, determine the change in its length and change in the dimension of its cross-section after applying the load. The material behave elastically. So you can see this is the bar, clear, and its length is 1.5 in the direction of Z. Its width is 100 millimeter and thickness is 50 millimeter. So this is the cross section. This is the dimension of this cross section, and P load is applied in the direction of Z. So you have to determine the change in length in the direction of change in the length in Z direction. Also, you can see due to this load, this thickness will reduce and this width will also reduce. So you have to determine the change in length in direction of y-axis as well as change in this width in the direction of x-axis. So let's start with the solution. So what will be the first step is that you can see this P is equal to 80 kilonewton is applied over this cross section. So area will be equal to, this is rectangular, so this width multiplied by thickness will give you area. So 100 millimeter in meter is 0.1 meter, and thickness is 50 millimeter, which is 0.05 meter, and it will give you square meter. Clear? Now we will first find the normal stress. Normal stress is equal to sigma, which will be in the direction of Z. So therefore I am writing sigma Z is equal to P divided by cross-sectional area. So P is 80 kilonewton. So 80 into 10 to the power 3 Newton divided by this area, which is 0.1 multiplied by 0.05 square meter. And when you solve this, you will get sigma Z will be equal to 16 into 10 to the power 6 Pascal. Now we have this stress. Now we know that also this sigma Z is equal to epsilon Z multiplied by modulus of elasticity of this material, which is A36 steel. So we do not have this E value. So how we'll get this E value? So you can get it by using this book. So at the end of this book, you can go to the property tables and you can see the average mechanical properties. Now you have this table. From this table, you can check it A36 steel. So its E value is 200 gigapascal, and we will also take the Poisson ratio value, which is nu. So this nu will be equal to 0.32. So I will write it over here that from average mechanical properties table, we get E of steel is 200 gigapascal, and Poisson ratio, which is represented as nu, and that nu was 0.32. Okay, so you have this E value. So using this equation, you can see that strain in Z direction is equal to sigma Z divided by E of steel. So you can have both the values. Sigma Z is 16 into 10 to the power 6 Pascal, and E is 200 gigapascal. So 200 into 10 to the power 9 Pascal. So when you calculate it, you will get strain in Z direction comes out to be 80 into 10 to the power minus 6. Either it will be dimensionless, or you can see millimeter per meter or meter per meter. So this is the value of strain in the Z direction or in the direction of the length. Now what we will find? We will find the first change in length, which is original length is 1.5. So change in the length in Z direction. We know that strain sigma Z is equal to change in length in Z direction divided by original length Z. Clear? So from here, this change in length in Z directions comes out to be epsilon Z multiplied by original length, which is LZ. So sigma Z, epsilon Z is 80 into 10 to the power minus 6 multiplied by this is length in Z direction. So I can write it, this is 1.5. So I can multiply it with 1.5 meter. So when you solve this, you will get change in length in Z direction comes out to be 120 into 10 to the power minus 6 meter, or epsilon Z, delta Z comes out to be 120 micrometer. This is the change in length of this bar. Now what we will do is that we will move toward finding the change in length in X direction and change in length in Z direction. As I have told you that due to this load P, there will be increase in length in Z direction, but this will cause decrease in this thickness and decrease in this width. So that can be obtained by using another formula, and we know that this Poisson ratio is equal to minus strain in lateral direction divided by strain in longitudinal direction. So again, I will show you that the strain in Z direction is longitudinal strain, and strain in the lateral that is perpendicular to this longitudinal, either in y direction or in x direction, will be the lateral strain. So from here we can write that we are going to find out this longitudinal this lateral strain. So we can see that this lateral strain will be equal to minus nu times longitudinal strain, which is now longitudinal strain, which we have find out, this longitudinal strain is equal to epsilon z, and these lateral strains are epsilon x and epsilon y, epsilon x and epsilon y, and both are equal. So we can write this, that this epsilon x is equal to epsilon y is equal to minus nu times epsilon z. So you have both the value. Epsilon is taken from this table, which is 0.32, so minus 0.32 multiplied by epsilon z is this one, which is 80 into 10 to the power minus 6. Okay, so when you solve this, you will get value will be minus 25 into 10 to the power minus 6, and the unit will be a meter per meter here, and that will be minus 25.6 micrometer per meter. This is epsilon x and is equal to epsilon y, strain in lateral direction. Now for finding changes in the dimension of cross section, or we know that this epsilon x is equal to change in direction of x divided by original length of this x. So this change in length of x will be equal to epsilon x into lx. Epsilon x is minus 25.6 into 10 to the power minus 6 multiplied by lx. So length in lx direction is this one. This is lx, which is 100 millimeter, or this is 100 millimeter is equal to 0.1 meter. So I can write 0.1 meter. Okay. So when you solve this, you will find the change in length in x direction of the cross section, which comes out to be minus 2.56 micrometer. Similarly, you can also find this change in length in y direction is equal to strain in y direction is equal to change in length in y direction divided by original length of y. So we can find this change in length in y direction is equal to epsilon y into length of y. So epsilon y is minus 25.6 into 10 to the power minus 6, and ly, length in y direction, this is y direction, so this length is equal to ly, 50 millimeter. So 50 millimeter is 0.05 meter. So when you solve this, you will get this change in length comes out to be minus 1.28 micrometer. So these are the answers about these questions. Okay, so this is the change in length in x direction, and these are the change in length of the cross-sectional dimension that is shown. And that was all about this problem, example 3.4. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. In this video, we are going to solve example 3.5 that is taken from chapter number 3, Mechanical Properties of Material, and book name is Mechanics of Material by RC Hibbeler, and it's 9th edition. So statement is, a specimen of titanium alloy is tested in torsion, and the shear stress strain diagram is shown in figure 3-25a. Determine the shear modulus G, the proportional limit, and the ultimate shear stress. Also determine the maximum distance D, the top of the block of this material shown in figure 3-25b could be displaced horizontally if the material behave elastically when acted upon by shear force V. What is the magnitude of V necessary to cause this displacement? So this is the stress, this is the shear stress and shear strain diagram for titanium alloy under the torsion that is tested, and we have to find the modulus of G, shear modulus G. We will find the proportional limit and the ultimate shear stress. And in part B, you can see this block. So there is a shear force applied at this face or surface, so you have to determine this displacement D, that this block will move due to this shear force. We also find the magnitude of V necessary to cause this displacement. So let's start with the solution. So first step is that we will find this shear modulus. So I will write it over here. Let me write it, shear modulus. So this value, let me write, this value represents the slope of straight line portion OA of shear stress versus shear strain diagram. The coordinate of point A on shear stress and shear diagrams are on x-axis, this is 0.008, and y-axis it is 52 ksi. So we can say that this shear modulus G will be equal to, you can see this is a straight line in which shear stress is directly proportional to shear stress. So we can also state that shear stress is directly proportional to shear strain. So shear stress is equal to G into gamma, and G will be equal to shear stress over gamma. So we can write shear stress over gamma, and for point A we will find this because G is in elastic region. Okay, so put the value of this. You can see this is point A. At this point we have, at proportional limit, we have shear stress is equal to 52 ksi, and at point A we have shear strain which is 0.008 radian. So you will put the value 52 ksi divided by 0.008 radian. So when you solve this, you will get this G will be equal to 6500 ksi, and this G is known as shear modulus, or it is also known as modulus of rigidity. Now we will find the proportional limit. So for proportional limit, this is the limit. Beyond this, this will not behave elastically. So what we will do is that, let me write first, by inspection of shear stress and shear strain diagram, this graph, the graph ceases to be linear at A. So this shear stress at proportional limit will be equal to, you can see this is your point A, and shear stress at proportional limit is 52 ksi. So we can write it at proportional limit shear stress is 52 ksi. And the last thing in this first part is ultimate stress. So ultimate shear stress is the maximum stress that this titanium bar bears under the torsion. So we can say that this value, this is the, you can see at point B, this value is the maximum value. This is TU, ultimate shear stress, and that is 73 ksi. So we can write directly that ultimate shear stress under this torsions comes out to be 73 ksi. So this is the answer of our first part. Now we will move towards second part, and in second part it is asked that determine the maximum distance d that top of the block if material behave elastically when acted upon by shear force V. So due to this shear force, this block will displace from this position till this, so we have to find this distance d. So we will write it, but it is given that this, if the material behave elastically, so we will play in this region, in this elastic region. So let's move and we will quickly see this. We will write it maximum elastic displacement and shear force. So what we will do is that, since the elastic shear strain, which is the maximum elastic, let me write it, maximum elastic shear strain is 0.008 radian, and a very small angle, the top of block, will be displaced horizontally. So you can see that this is the maximum shear strain in elastic region that will, this titanium alloy specimen will bear under the shear stress. So we will write this clear, and we know that this is the angle, this is given as shear strain, which is the change in angle in right angle triangle. Initially it was perpendicular, but due to the application of this load, it will change this angle. So this angle is known as shear strain, and this maximum shear strain in elastic region is 0.008. So what if I take tangent of this shear strain gamma, that will be equal to perpendicular over base, so d over 2. I will write it downward. So tangent of gamma is equal to d divided by 2. So from here, this d will be equal to 2 times tangent of gamma, and 2 multiplied by tangent of gamma is 0.008 radian. And when you multiply this, you will get this displacement d due to the action of shear force, which comes out to be 0.016 inch. Now we have this, the answer of second part. We will find this shear force which will cause this displacement d. Clear? So how we will find this? We know that the third part is, we know that this shear stress, average shear stress, is equal to shear force divided by shearing area. So we can see that in elastic region, the maximum shear stress is this one, which is 52 ksi over this area. This is the area over which it acts. So it is 3 multiplied by 4. Clear? So we will write it that V is equal to average shear stress into area. So average shear stress is 52 ksi. So I will write 52 ksi multiplied by area is 4 multiplied by 3 inch square. Clear? So we will get this V. So when you solve this, you will get the shear force V will be equal to 624 kip. And this 624 kips shear force is necessary to move this displacement D is equal to 0.016 inch. And that is all about this example problem 3.5. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. In this video, we are going to solve example 3.6 that is taken from chapter number 3, Mechanical Properties of Material, and book name is Mechanics of Material by RC Hibbeler, 9th edition. So statement is an aluminum specimen shown in figure 3-26 has a diameter of 25 millimeter and gauge length of 250 millimeter. If force of 165 kilonewton elongates the gauge length by 1.20 millimeter, determine the modulus of elasticity and also determine by how much force causes the diameter of specimen to contract. Take modulus of elasticity. A modulus of rigidity of aluminum is 26 gigapascal and yield stress is 440 megapascal. So you can see this is a tensile test specimen for aluminum. This is the gauge length, which is L0 and given as 250 millimeter. The diameter of this specimen or gauge length is D0, which is equal to 25 millimeter, and 165 kilonewton load is applied. So due to this load, there is elongation in this gauge length, and this change in length, for example, this change in elongation is equal to 1.20 meter. So you have to determine the modulus of elasticity, and due to this load, the length will increase, but diameter will contract. So you under this load, how much this diameter contracts. So we have to determine that contraction as well. So let's start with the solution. So first thing is that we have to find the modulus of elasticity, and we know that modulus of elasticity is represented as E, and this is, as we know that by Hooke's law, stress is equal to modulus of elasticity into strain. So E is equal to stress over strain. So first we will find this normal stress. So normal stress due to this force of 165 kilonewton will be equal to force which is F over A. So F is 165 kilonewton, so 165 into 10 to the power 3 newton, and the diameter of this is given as 25 millimeters. So diameter area of cross-sectional area of this circular cross-section will be equal to pi by 4 d square. So pi by 4, and d is 25 millimeters, so in meter it is 0.025 square. So when you solve this, you will get stress will be normal stress will be equal to 336.1 megapascal. Now we'll find this, we have find out this, we will find strain. So we know that strain is equal to change in length over original length. So change in length is this one, 1.20 millimeter. So I will write 1.20 millimeter divided by original length, which is 250 millimeter. So 250 millimeter. So when you solve this, you will get 0.00480, and it will be either dimensionless, or you can also write as millimeter per millimeter. Clear? Now we have both this value, so put it in this equation. E is equal to stress over strain. So E is 336.1 into 10 to the power 6 Pascal divided by strain is 0.00480. So when you solve this, you will get 70 gigapascal. So this is the answer of our first part. Now we'll move towards second part, in which we will see that due to this load of 155 kilonewton, there will be how much contraction is in this original diameter D0. So we'll move toward that contraction of diameter. Now we will find this contraction of diameter by using this equation that we know that Poisson ratio is equal to lateral strain over longitudinal strain. So we have this longitudinal strain, but we do not have lateral strain. So how we'll find this? We also know that there is an equation relationship between modulus of elasticity Eg, which is modulus of rigidity, and Poisson ratio nu. So what is this equation? This equation is G is equal to E over 2 divided by 2 into 1 plus nu. Clear? We have all this value. You can see G and G is given. E we have find out 70 gigapascal. So we'll find this nu. So G is 26 gigapascal. So I will write 26 gigapascal. E is 70 gigapascal divided by 2 into 1 plus nu. Clear? And from here you will get this 2 into 1 plus nu is equal to 70 gigapascal divided by 26 gigapascal. And 2 plus 2 nu is equal to 70 divided by 26. So we are interested to find out nu. So 2 nu will be equal to 70 divided by 26 minus 2. And if you divide 2 on both sides, so you will get Poisson ratio, and it will be equal to 70 divided by 26 minus 2. Clear? And when you calculate it, you will get this Poisson ratio comes out to be 0.347. Now you have this value, you can just plug it in this. So we will get the lateral strain. So we will, from here, we know that lateral strain will be equal to minus nu times longitudinal strain. Longitudinal strain is the strain along the length of the specimen. So minus 0.347 multiplied by longitudinal strain is this one, which is 0.00480. And when you solve this, you will get this lateral strain will be equal to minus 0.00166 millimeter per millimeter. Now this lateral strain is perpendicular to the longitudinal strain. So longitudinal strain will be in this direction, and lateral strain will be in this direction, which is causing to contract the diameter. Now what we will do is that we will find the contraction in diameter. So contraction of diameter is, therefore we know that lateral strain is equal to change in diameter, which is delta D divided by original diameter D0. So this change in diameter or contraction is equal to lateral strain multiplied by D0. So minus 0.00166 multiplied by 25 millimeter will give you minus 0.0416 millimeter. So this minus sign means that there is a contraction of 0.0416 millimeter in diameter. So the diameter will contract by this amount here, which is the answer of our this second part. And that was all about this example problem 3-6. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching.